Hi, I'm Bridget. I'm a PhD student here at the University of Birmingham in the Department of Earth Sciences, and I'm studying these n-alkane things. So what are n-alkanes? N-alkanes are what we call a geologic biomarker. That is a molecule that's really resistant to degradation and preserves very well in the geologic record, so we can see how it changes through time. N-alkanes in particular are known to change with environmental conditions. So they're really useful for paleoclimate because you can look at how they change through time in the sediment core and use that as a record of your past climate. The particular facet of n-alkanes I'm looking at today is the ACL, or the average chain length. And that's just the average number of carbons in your n-alkane chains that you find in a sample. So why might ACL say something interesting in the geologic record? And that's because of what n-alkanes do. Very long chained n-alkanes, with something like 27 to 31 carbons in the chain, are produced only by higher plants as part of a protective layer on the surfaces of plants used primarily to conserve water. Longer chain lengths are better at doing this than shorter ones, but they take more energy to produce. So we know from modern data that on average, plants growing in hot, dry environments have a higher ACL, more carbons in their chain, than ones in cold, wet environments that need to conserve water less. And there's a big dose of things like phylogeny and growth form, which affect it as well. So where does elevated CO2 come into this? Well, elevated CO2 may decrease the amount of water that plants need a bit. So they might need the protection of their n-alkanes less, so we might see a decrease in ACL. And if we do, this means we need to reevaluate some of our interpretations of n-alkanes in the geologic record, which normally get put down to temperature or changes in vegetation type. So what have I found? It's good news for the geologic status quo. With my BI4 data here, I've got 4 years of data from Acer pseudoplatanus, that's sycamore at BI4 from 2017 to 2020. And at this point, it's pretty conclusive that at BI4, there is no influence of elevated CO2 on n-alkane ACL at all. This data covers 4 years, and there's no change in 2017, and there's still no change in the 2020 data, so it's not changing over the few years of time I have here. So we can conclude from this that if ACL changes with CO2, it needs more than 4 years to start doing so. So ACL does not change with CO2 in any meaningful sense in my data, so it doesn't need to take into account in the reconstructions of ACL on the paleo record with the data I have. However, all this confirms is that leaf wax ACL doesn't change rapidly with CO2 within plants that are already growing. Not that it doesn't change between multiple generations of trees, which might be important for geologists, or, as also might be important for geologists, might change with evolution and evolutionary time. So my future work is going to be looking at proxy CO2 reconstructions and seeing if there's a link between ACL and reconstructed CO2 on the timescale of millions of years.